All right, all, welcome. Sorry we're running a tad late, but thank you for coming, and thank you for coming for the AIA Building Science Committee event. We're going to kick off tonight with resilience to extreme weather events, and today we have our moderator who's going to introduce all the speakers, and we'll just get starting. So less of me, more of them. Go ahead.
Good evening, everyone. My name is Leonie Garbus, and I'm a Senior Project Manager at Simpson Gumpertz & Hager, SGH. And on our panel today, we'll have Daniel Kinsley, an Associate at GMS, Jessica Mandrick, a partner at GMS, and Edward Tang, Founding Principal at Tang Studio Architect. I'll get into their bios a little bit later. First, the obligatory AIA slides. You're going to get credit for this. You signed up. We have your information. If you did not sign up and you're here, that's okay too. Just make sure you get us your information somehow so we can get you credit. We are going to be talking about resilient design and in particular with flood and hurricane mitigation projects in New York City. And here are the learning objectives. I won't read them. Hopefully you're here so you've read them and you know what we'll be going through. So like I mentioned, I'm a Senior Project Manager at SGH, particularly focusing on the building enclosure, building technology side of things. A mix of new design, investigation, rehabilitation, and custom glazing systems. Edwin Tang is the founding principal at Tang Studio Architect, and he sits on committees for New York City Construction Code Revision and ASC 24. He is certified floodplain manager with the Association of State Floodplain Managers. Daniel Kinsley is an associate at GMS. He's in the Building Envelope Consulting Group at GMS and has worked on a wide variety of projects, including facade restoration, repositioning, overcladding, as well as new construction in the commercial and residential markets, featuring designs in curtain wall, precast, and masonry. And last but not least, we have Jessica Mandrick, a partner at GMS, who has provided structural engineering services for numerous buildings located in hurricane and flood hazard areas. She served on ASC 24 Urban Flood Study Team after Hurricane Sandy and assisted with Sandy recovery efforts. She is a vice chair of the ASC 24 Flood Resistant Design and Construction Committee, a member of the ASC 722 Flood Load Subcommittee, and Vice Chair of the New York City Building Code Flood Resistant Construction Committee. So we have a nice variety of team members chatting with you today. We'll be going through resilient designs, some climate change and hazards, historic trends and projections, and future developments as an introduction into the theme of resiliency and climate change. So why do we need resilient design? Well, I'm sure, especially for those of you who are from New York and in New York, you've noticed that we have stronger storms and coastal flooding in higher frequencies and more intensity than in the past. And what is resiliency? Well, it's the process of designing buildings and structures to withstand and quickly recover the impact of extreme weather events. Historic weather data does not accurately represent the climate change projections. We have to incorporate response planning as part of resilient design. And then there's a portion of resilient design which includes recovery design for how the building will recover, but also how the community as a whole will recover. There are multiple hazards. As I mentioned earlier, we'll be focusing on flood and wind tonight, including rain, because that affects flooding and is often in combination with high wind events. So here are some historic trends for sea level rise, as well as projections for New York City. And the sea level is expected to keep rising by 11 to 21 inches, so almost 2 feet by 2050, and 18 to 39 inches by 2080. With precipitation, right? We see the similar trends. They're increasing through the years. And the mean annual precipitation in New York City is projected to increase between 4 to 13% by 2050, and by 5 to 19% by 2080. And we've seen these storms, right? Winds and high winds and intense storms. And we anticipate that they will continue to increase in frequency and intensity through the years. As I mentioned, current codes are primarily based on historic data. They don't account for these projections. They don't account for the trends we've all been seeing and living in recent years. There are, however, codes and standards that, committees in the process of accounting for these future projections. They're just not quite there yet. So we're anticipating in 2028 an addition of ASC 7, which provides loads for designing structure and components and cladding, and that this version will include some of these projections for changes we've been seeing in flood and snow and rain and ice and wind. So that's kind of what the future holds. This is your introduction to hazards and climate change, and I will pass it on to Edwin for his portion of the presentation.
Thank you, Leonie, and good evening, everyone. I'm Edwin Tang from Tang Studio. I run an architectural and consulting practice, and today I'm going to run you through some of the projects and approaches I take when dealing with buildings in flood hazard areas. So first of all, compliance, right? Every design professional, every owner runs up against compliance requirements, and I think the city planning department has a very good guide for the design industry on how to approach a project that is located in a flood hazard area. So first of all, you need to know, am I in the flood zone? How high is the amount of flood risk that my site is facing? And then you need to understand what are the layers of regulatory requirements that apply to my site. And once you understand that, you need to see what are my options for making my site and my building a flood resilient building. And then you get into the details of how do I design for it. So first of all, you've probably seen this before, the FEMA flood maps. So you can see here the blue dots being the V zones and the A zones where there's a flood hazard risk, a 500-year base floodplain, a 100-year floodplain, and then you have the black dots, which is a shaded X zone. So as you go inland, the amount of risk subsides. So from the flood maps, you know where you are, you know the elevation of the water that you have. So as a design professional, there's some other pieces of information we have to collect. We need to know the grade elevation that your site is situated on. And also, you need to know the codes. The current codes have been revised. Pretty much whatever your flood zone is, the codes require a amount of freeboard that usually is 2 feet for most occupancies. And you basically subtract from your flood map the grade elevation to determine how much water, how high the water will be against your building envelope. And that's called flood depth. So here's a project that I worked on. It's on the west side of Manhattan. It's a slope site. So from the maps, I know that my design flood elevation is 14. So what I did is I added 2 to the base flood elevation of 12 that I read off of the map. Then I looked at the architectural survey for the grade elevations. So you can see the black numbers as the grade elevations, and you can see that as you go inland, the land is higher. The blue represents the flood depth, which basically is the design flood elevation minus the grade elevation. That's how high the water is. There's a point where it becomes 0 as you're midway uphill. That's the 0, 0. And then the negative just means the water will never reach that area of the site. So this is how you, first of all, understand how high the water is around your building. Then you look at the relevant regulations, and there are quite a few. So it starts at the federal level with FEMA and the National Flood Insurance Program. They publish a series of rules. a series of guides for what you can and cannot do to qualify for flood insurance, which is required for sites located in flood hazard areas. Then at the state level, sometimes it does impact a project if you're located near tidal wetlands, freshwater wetlands. There's additional regulatory hurdles to go through. And the local level is where it's usually the most intense. You're dealing with the regulatory agencies of New York City, the buildings department, the fire department, transportation, and also city planning for zoning. So as far as identifying your adaptation strategy, at a very high level, there's two categories of projects. Those that are that trigger compliance by the nature of the work, which is either new construction or buildings that are substantially damaged or substantially improved. If you're in that category, the standards and codes apply to you. So for residential uses and non-residential uses, you can always elevate your lowest occupied floor to be above flood elevation. But when it comes to intervention measures for flood resiliency, if you have spaces located below design flood elevation for residential, your options are very few. You can only wet flood proof, and you can only have spaces that are parking, storage, and building access. Basically no occupied spaces. If you have commercial, for example, or other non-residential uses that are below grade, your only option really is to dry flood proof. And we'll go into what wet flood proofing and dry flood proofing means, but it's important to understand that you can always elevate, and that's the passive approach. Now, there's also a category called voluntary flood hardening, and that's when you have a building that doesn't trigger compliance, meaning that the scope or the area of work is small. You're in a flood zone, but because your scope is so small, you're not forced by the codes to comply. And in those instances, as a building owner, they still want to have some protection. And in the old days, it was the sandbags. Nowadays, there's a lot more products on the market that allow buildings to protect themselves. And in that category of voluntary, you are a little more free to choose different options because it's not required. It's more of a voluntary approach. So all these options of wet flood proofing, dry flood proofing, and elevation are available. So just to kind of quickly review, what does it mean to wet flood proof a building? Essentially, you're letting the water in to the building. And the reason you do that is a lot of these existing buildings or structures that are designed before flood regulations came into play were not designed for lateral loads from water. Hydrostatic pressure, hydrodynamic pressure, floating objects that may impact the side of your building that's not designed for seismic or any kind of lateral. And if you don't do this, what happens is water will build up on one side, the exterior, and exert a pressure against the building wall that may cause it to collapse. And in order to avoid that, wet flood proofing mitigates that uneven pressure to create a balance so that you don't have uneven loading against the wall. And the way they do that is with the use of flood openings or flood vents that are basically passive devices that allow water to flow in and out automatically without any sort of intervention. So here's a photo from one of the suppliers of flood vents on the market. It's showing you a building that lets the water in and out passively with vents. And the vents have evolved to have more options. Some are insulated, some are ventilated, some are fire rated in certain instances that require fire separation. And these are all passive. The way they work there's a formula based on how much water is anticipated, the area within the building that needs to flood, and the formula basically tells you how many of these openings you need to provide along your facade. So here, the standard is you always have to have 2 openings. They normally need to be on 2 separate walls, and that's to prevent them from clogging or getting blocked. It's just a kind of a backup. And a lot of times, depending on how much area is inside the building that needs to be protected, one vent may not be enough. You may need to stack them in an array and have multiple openings to meet the required area. And then dry floodproofing. It's just the opposite. Don't let the water in, keep it out. And you're keeping the spaces dry that are located below the flood elevation. And that's not only above grade, but also below grade. So these are more involved as far as structural design. You need to make sure the building can take the loads. And there are basically 4 types of load from ASC 7 that apply to these situations. It's hydrostatic, which is still water, hydrodynamic, which is waves, impact loads, floating logs, floating vehicles, and then you have wind loads too. So when you design, you talk to the structural team, as they design it, they have to apply all these loads simultaneously. So there are 2 categories of dry floodproofing options on the market. They're broadly categorized as active measures on the right, which require human intervention, requires a flood emergency plan. And then you have passive options, which do not require human intervention. They basically are a set it and forget it. Like you have the flood barriers that are embedded into the grade, and they're actuated by water. The rising water will cause this gate to lift automatically. And you have flood resilient glazing, which is just, nothing to do. It doesn't move, no moving parts. So from my experience dealing with projects, both from the regulatory side at the city and also in private, is most building owners will elect to use flood shields because they are the most economical, the least disruptive as far as architectural impacts to the facade. And also, they are kind of simple to install. So I'm going to speak a little more about temporary removable flood shields on the very first on the left. These are usually aluminum planks to be lightweight, so that it's easy to carry out of storage, and they have rubber gaskets all around them. When you elect to use this option for protecting your building, you're required to provide a flood emergency plan, which is a big manual that shows you, and I'll give you an example at the end of what it means. But basically, it requires drills, requires storage, tools, and trained personnel to deploy them and when to deploy them. There's so many of vendors of these products right now. They're examples of how you can architecturally hide the embeds because they attach to the building, both on the walls and also where the spans are longer, there are intermediate posts with embeds usually in the sidewalk. So here are some kind of details for connections to the facade, to the sidewalk. These are all usually engineered by the vendor and suited to be compatible with the architectural materials and language of your facade. So once you know the strategies that are available for you as a design professional for your project, you have to design your building. So here's an example of a mixed-use building. You have retail on the ground floor, you have residential on top. So as we apply the concepts, you can only dry flood-proof commercial. So you see the flood shields, and you're required to maintain egress after the flood shields are up. So you have those crossover stairs. And then the elevation, the residential units are elevated. And then the lobby, of course, needs to be wet flood-proofed. And any subgrade spaces can only be for commercial use because you're not allowed to dry flood-proof residential where you are triggered to comply. Again, if it's voluntary, you have a little more leeway. So let's look at a real project that I worked on. This is a new development in Brooklyn. It's a double corner lot. It's residential with ground floor retail. So again, it's a new construction, so we have to comply. We don't have a choice. So residential needs to be wet flood proofed, residential portions and spaces in the building, and non-residential spaces can only be dry flood proofed. So you can see the blue shaded overlay is the base flood elevation based on the FEMA map before you apply your +2 of freeboard. So once you apply the +2, you can imagine that the whole site is going to be blue. It's going to be underwater. The red represents the temporary flood shields over every single retail entrance, and they come with crossover stairs, which are required for emergency response and also for egress. And then you have the areas with the blue arrows. Those are the residential lobbies and exits. By code and by the standard, they have to be wet flood-proofed, which means water is allowed to be going in and out without human intervention. So they will have flood vents at the doors, at the glazing, at the envelope. And here is, there was also an MTA easement at the middle of the building. So just as an example, which also is to be dry flood proofed. So we have those flood shields. The design elevation is 2 feet above grade, the flood depth. So two planks and the crossover stairs. Here's a sample of how the residential lobbies would flood proof or wet flood proof their spaces with the use of flood vents. At the facade and at the base of the doors. They didn't actually put punch holes in glazing at the bottom of the door. What they did was they made the bottom panel solid, just cost and also just practicality. Here's another case of a new development in the Rockaways. This is a affordable housing mixed-use development, HPD project. Here, it's interesting. It's also mixed use. All the pink are the commercial retail spaces. All the blue are the residential lobbies. So same concept. You have a mixed approach, dry floodproofing and wet floodproofing. And the interesting thing for this project is because it's a government subsidized or government funded project, they elected to plan for future sea level rise. So the design flood elevation is a minimum. It doesn't mean you can't go above it. So the solid blue line is the code minimum design flood elevation that you have to design to. The dashed blue line is what this project owner decided to protect against. So it's a good 6 feet above the minimum, planning ahead for the future. So their residential areas are wet flood proof to 6 feet above the minimum. And then the red is the commercial spaces because of tenant sensitivity, commercial tenants who, insurance concerns, they chose to go even further and they went up to 8 feet above the minimum. So this is showing you how there are projects who will go above and beyond code. And the other reason was it ties into the zoning floor area calculations as well because wet flood-proof spaces have a lot of options for floor area deductions. So by deducting entire levels on grade, you can get additional floors, additional square footage for the project. There are some gaps right now. A lot of the regulations deal with coastal flooding. Well, here's another case that I worked on, a project that's in a shaded X zone where there is no base flood elevation on the maps, and there's no code requirement to provide flood proofing, unless you're like institutional hospital occupancy. This is a residential mixed-use occupancy. They technically didn't need to provide flood proofing, but they are located right at the boundary between an X zone and A zone, which has a flood elevation and has requirements. So when you overlay the base flood elevation of the neighboring A zone against this site, you see that the corner of the site is actually subject to flooding, even though by code you're not needed. Yes?
I just had a quick question on the previous slide, the boundary there. I don't know how to visually represent any error in the boundary. How do you think about the fact that some estimates might put the boundary further from the site, some estimates might put the boundary away from the site?
So yes, that's a very good question. There are current FEMA maps. There are preliminary FEMA maps, which are post-Sandy. I think the first thing you do is look at both because the code in Appendix G will say the more stringent one governs. So first of all, whichever map shows your site in the blue, you have to kind of, that will determine, do I need to even consider this? Once you are in the blue, then you have to look at your architectural survey, figure out the grade elevations. Is your site subject to flooding? And not before construction, after construction, because your project may involve some regrading So you need to know whether you are in the zone. So I would say the survey would be the most important.
That's super helpful, thank you.
Yeah.
Insurance issues are also there.
Excuse me?
Insurance issues also there.
There's an insurance issue there?
Oh, yeah, insurance issue, for sure. Yeah. So here, the project, the client decided, per my recommendation, to provide for this reality because your project is subject to flood, even though your map says you're not. So this is kind of a little interesting gap that, is there. So a lot of the FEMA maps are talking about coastal flooding, sea level rise in storms. But the reality is, and you may have heard in the news, that there are instances where there's flash flooding inland away from the coast, and the FEMA maps will not cover this. New York City has started to map these areas based on incidents, and currently you have low risk, and then as you kind of go with the projections to extreme in 2080, you really see a lot of pockets of inland areas that are subject to flooding, serious flooding. And that's currently not in the regulations. There are efforts throughout to start to kind of plan for this. So first being, especially HPD projects, where they elect for enterprise green community incentives, there is a design criteria for stormwater management. So you need to design for your site. If it's really sloped, there are driveways going underground, you need to deal with that anticipated storm flow. The city also has a unified stormwater rule, a DEP. That's more geared towards infrastructure and streets. There's no direct mandate on a specific site to deal with this. There are also efforts from nonprofit groups to develop recommendations for how to better address flash flooding in the city, in partnership with the city's mayor's office as well. There's an effort with Rainproof NYC to start to develop criteria for how to protect against this. There's some challenges. I'm going to touch on a couple challenges that I've been dealing with. Here's an example of a flood emergency plan for flood shields, temporary flood shields. So this is a very big challenge because it's a very intricate production. A deployment of flood shields, it's like a Broadway production. You need to rehearse. You need to get your supplies, your actors in place, and then it sits idle for years sometimes. And then people turn over, the gaskets are worn out after a few years, they don't work, someone lost a few pieces. What good is it if you spend all this money as an owner to provide this, but then it doesn't work when you really need it to? I would say that's probably the biggest challenge that I've seen across many projects. And this is a flood emergency plan, just to show you the scale of it. There's so many moving parts, so many things that have to be checked on and kept in fitness and readiness at all times. And this is just another kind of interesting case that I deal with a lot on projects in the city. I mentioned earlier when you have flood vents for wet floodproofing, they have to be on 2 walls. Well, you have a lot of attached buildings in New York City. There's only 1 wall, so what do? I don't have 2 walls. Or I'm on a sloped site where the back wall is higher and the flood water will never get to the back. So what good is it if I put my flood vent in the back? So we made a proposal in ASC 24 to allow certain instances where there's only 1 wall that makes sense to put all the flood vents in that 1 wall. So with that, I'm going to turn it over to my colleague here, Daniel. Thank you.
Thanks, Edwin. That was great. Hi, I'm Dan Kinsley. I'm an associate in the Building Envelope Group at GMS. Edwin just walked us through kind of the general approach to determining your flood-resistant construction is required and how we determine it. And I'm going to walk you through some actual project examples, how we address these requirements. We're going to look at both wet and dry flood proofing, specifically as it relates to ground floor glazing. Okay. So again, Edwin walked us through the firm map, so I'm not going to reiterate. But this is a segment along the west side of Manhattan. This area has seen a significant increase of new development over the past few years. And as you can see, much of the area is in an AE zone. I'm going to touch on three projects my office worked on in this stretch recently, and the flood mitigation solutions that we used at the ground floors. So wet flood proofing, we talked about this a little bit. As we heard earlier, the rising floodwaters apply pressure to a building structure and cause damage. The hydrostatic pressure of water pressing against a foundation can cause entire homes to dislodge from their foundations during storms. The concept of wet flood proofing is to eliminate that one directional pressure on a building and allow the water to get to both sides of the wall and therefore equally distribute that pressure and rise equally on both sides. As you can see in the somehow rotated picture, that doesn't make any sense. That's a residential door that has a flood vent in it, right? So that's one thing we talked about. So this first project I'm going to talk about is a residential project with ground floor retail. We spoke about the residential spaces requiring wet flood proofing and commercial spaces having the choice to pursue wet or dry flood proofing. In this project, the architect and the owner elected to use a wet flood proofing strategy across the entirety of the ground floor, so both at residential requirements as well as commercial spaces. If you look at the partial ground floor plan on the left, you can see that the exterior wall dashed in red, and above that highlighted in yellow is something labeled the flood wall. There's a flood wall inside the building. So if you look on the right now, you notice that the exterior glazing sits on a curb below our design flood elevation, right? And rests on a concrete curb. When the flood waters rise and the hydrostatic loads reach a certain level, the flood vents in the curb open and allow the water to enter the building. The hydrostatic pressure on the facade is removed and the water rises equally on both sides. The strategy allows for a less robust wall construction and glazing assembly. What is interesting here is the flood wall on the interior. The flood vents allow the water to enter the building, but the flood wall, which is about 42 inches tall at this location, extends up to DFE and about an inch past, prevents this flood water that enters the building from entering the entire building and damaging interiors and other precious things in the inside. So here the owner made the choice to sacrifice the first 2 feet of the building interior to protect everything beyond it, right? But also have the lesser expense of building something a little less robust and bringing glazing down closer to the facade, which is to grade, which is much more common here, rather than having it sit up 3.5, 4 feet above grade. Lastly, on this slide, I'll point you to this stone cladding panel here that you see. That's set in front of our flood vents and our wall. So this is the finished example. What you'll see is the glazing comes down on top of the curb down to grade below DFE, and the architect didn't want to see the flood vents, right? They didn't think that was aesthetically pleasing. So what they did is they put this stone cladding in front of the flood vents and perforated it with several holes that would allow the water to fill in past the stone, fill up the cavity, and then trigger the flood vents and allow the flood waters in the building. So kind of clever. All right. Now, some of you may be more well-versed in the wet flood proofing, so I'm going to spend some time on dry flood proofing applications specific to glazing systems, as it is becoming increasingly popular to use this method. Dry flood proofing is, as you imagine, strategies for resisting floodwaters and preventing water from entering our buildings. In some cases, a site's designated flood elevation may be 3 or 4 or 5 feet above street level, typically meaning 5 feet of opaque surface. Back in 2020, the New York City Building Department, through their Office of Technical Certification and Research, issued a building bulletin to address the increasing interest in using glazing systems as perimeter barriers for floodwaters. The building bulletin established evaluation criteria for glazing systems using dry flood proofing in special flood areas, also known as flood-resistant glazing systems, designed to meet the definition of substantially impermeable and to resist the site-specific design loads pursuant to ASC 24. The main performance criteria referenced in that bulletin is set forth in ANSI FM 2510. Right? ANSI is the American National Standards Institute, and they partnered with this standard with Factory Mutual Standards, or FM Standards. FM Standards is a research and testing arm of FM Global, a major international property insurance provider. FM Standards independently researches, tests, and certifies products used to protect facilities. We're going to take a look at two project examples that took slightly different approaches to meet this requirement. First, the first project has a pre-tested solution, and I'll get into what that means. The project is currently in construction. It is a residential project with ground floor retail. On the plan, the blue areas are residential areas that require wet flood proofing, so there's flood vents or flood barriers. And the red areas are areas that are commercial areas that are protected by dry flood proofing. The green areas have no requirement. The key to this project is using a previously tested system. And I will get to that in a second. In this section, the detail you see is an example of the calculations put together for a site-specific loading diagram here. The hydrostatic loads, the hydrodynamic loads, the debris loads, all pre-calculated before we get into design. And our next speaker, Jessica, will get a little more into that. So, here, system design. In the section detail to the right, you can see two systems separated by a steel tube. The steel is set 1 foot above the designated flood elevation for the project. In dry flood proofing applications, if that's the route you choose to go, is required that you set your dry flood proofing area 1 foot above DFE. Below the steel, you have a structurally glazed, flood-resistant glazing system. And above, you have a more typical captured glazing system of a typical, more conventional storefront system. The architect could have chosen to extend the FRG to the full height of the opening, beyond DFE +1, but that would have been costly. So instead, we separated the systems to create, but they're designed to look similar, right? Rather than paying the cost to have the full flood-resistant glazing all the way up, we separated them to decrease the cost. Moving to detail on the top left, the first thing you may notice is the thick glazing assembly. The architect had chose to, wrong spot there. Per the FM ANSI standard, as I mentioned earlier, the laminated glazing is required within flood-resistant glazing systems. The standard says glass is allowed to crack during a flood event, but not shatter. So that's mostly due to the debris. Here we have an interior light, right, on the top side, laminated with an SGP inner layer. That's really the workhorse. That's what's keeping the flood loads out of the building, right? That's doing all the work. And the exterior light, some monolithic glass, is carrying a low E coating, and it matches the rest of the glass on the building. So the aesthetic from the exterior is still going to look the same, but you get the protection that you need. The framing system is a rather typical aluminum system on the top and bottom. And the reason, the framing system has been previously tested against certain loads, and therefore the project lab testing is not required. The OTCR bulletin that I previously mentioned states that if a proposed system is factory tested for loading equal to or higher than that expected at your site, project-specific testing can be waived. Right? That said, a mock-up for this particular project is going to be done because the owner is just interested in that protection. Now, what if you wanted you didn't have a pre-tested system that worked for you, whether the loads that you have on your site or aesthetics? Right? This is a commercial office project with ground floor lobbies and retail. It's an existing building that was renovated and expanded upon. Per the building code, alterations to pre-firm buildings that increase their non-compliance to flood mitigation codes are required to become compliant. This building, originally built in 1934, so well before firms were established in New York City in 1983. The areas highlighted in yellow are areas where custom flood-resistant glazing was used to meet these requirements. There are other areas of the building that were wet flood-proofed or just used concrete walls, but these were the retail spaces. For the project, DFE is about 5 feet above grade. That's in some locations. Some of those locations were designated for retail, and the architect and the owner did not want 6 feet of opaque space surfaces before vision glass started. Prospective retail tenants would prefer pedestrians could look into their spaces from the sidewalk, which is understandable. This meant lowering the sill of the existing openings below DFE and a custom storefront system to meet the flood loads. The system is structurally glazed with steel mullions. The steel is more robust than your stock aluminum extrusions and can handle the heavy loads that were calculated for this site, plus the wide spans. We had some openings that were 20, 22 feet. The glazing resists the loads, transfers it to the steel, and the steel transfers it to the columns and the flood walls that surround them. There's an aluminum extrusion beauty cap that was adhered to the glazing to match the aesthetic of the standard storefront above that has your standard extruded beauty cap. And unlike the pre-tested system, there were more options and customizations here. It just meant it had to be tested. So that's what we did. The OTCR bulletin requires lab flood load testing if the system is not pre-tested, as I mentioned, right, according to the ANSI FM standard. For this project, a mock-up was constructed, a custom mock-up, and installed in a testing laboratory. In the photo, we're looking at the interior surface of the glazing system, right? The exterior side is inside of a steel bathtub and where the testing is going to go on. So the protocol asks for 2 tests required for this specimen, a hydrostatic bathtub test and a debris impact test. So as you can see on the left, you can see the tub being filled with water. The water is left there to rest against your system for 24 hours, and they measure the leakage that comes through the system. The allowable leakage is less than a tenth of a gallon per hour per linear foot, so very little. There is an allowable amount as nothing is deemed impenetrable, so they do allow you a small amount to leak through. Once we pass that, you move on to the debris impact test. And what you see here is they're simulating a telephone pole. So what they've done is they've taken a piece of wood and they've mounted it to this metal hammer, and they lift it up, they take it onto a lift, and they put it inside the tub, and they actually just drop it. It's very, very simple. They just drop it against the glass, and sure enough, the glass breaks, the outer light breaks, and there was some small cracks on the inner laminated light, but that was to be expected. And once that's done, they fill the tub back up with water, and they let it sit for another 24 hours, and they again test the leakage, because even after the damage, the system still has to perform. Okay, now the testing is complete. These units start to be fabricated and installed out in the site. On the exterior, you can see the location of DFE +1, and that's the separation of our system. And you can see the separation of the flood glazing and the typical system. And from the exterior, they look pretty much the same. During a flood event, the flood-resistant glazing transfers the load to the columns, as I said. And in this case, the loads that were calculated were rather high, and we have this double height cellar space in one retail space, so that the sidewalk is actually right up here. And because of the loads that were calculated and how this structure was built, they actually added concrete buttresses to reinforce the columns in one side of the building. So these are just a couple of finished photos from the exterior. As you can see afterward, you can see where the DFE is. You can see the separation between our flood-resistant glazing system and then a typical stone-clad concrete wall. It actually came out pretty good, I think. And it looks pretty seamless with the typical storefront above. That's all I got. Next up is Jessica. Just give us the structural engineer's perspective on all of this.
Hello, everyone. I'm going to talk a little bit about some of the structural implications for designing in flood and hurricane regions and some of the upcoming code changes that you might see. This is an image of a flood load diagram. We've seen a few of these before. One thing I want to point out, grade is up here, but after the flood, grade is down here. I think one thing people don't always consider is the erosion that happens during a storm. And in structural design, this is one of the most critical elements, because when piles become exposed, their capacity to resist lateral loads drops. The pile is in bending. The bending of the pile controls the design of the pile. you need a lot more piles to withstand the lateral load. In most of the projects that I've done, the controlling factor for flood design is what lateral load the foundations can resist. In terms of a dry flood-proof structure, we talk about buoyancy. In order to resist uplift, to prevent the structure from floating like a boat, the concrete is tied down to the piles with a tension connection. This is an example in a wood pile of a tension attachment. These plates are bolted through the pile. You can stick up to a number 10 rebar through the holes in the plates and engage the piles if there's an uplift force on the foundation. If your building doesn't weigh enough that you have the weight to resist it from floating. For piles, typical construction in a coastal area is a timber pile. Timber piles may not have the bending strength to have this elevation of the soil scoured. This is an example of a cast-in-place concrete auger cast pile. You can see there's a cage for the top 20 feet. This pile had about 5 times the lateral rated capacity as the timber pile in the same scour conditions. This is an example of a dry flood-proofed structure. This is a bunker. You can see here this is the mat foundation. There's a rat slab poured. The rat slab is waterproofed, and the mat foundation is placed above the waterproofing. You can see rebar that's extending up into the mat. These are connected down stirrups that connect to concrete surrounding the piles to engage the piles for uplift. You can see in the background there's an opening for a door. If you're doing a dry flood-proof space, a bunker below grade, you can use a flood-resistant door. They look like a submarine hatch. And you can see that any openings out of this mechanical space are at the top of the walls. They're above the design flood elevation. In a hurricane, the glazing is often designed to be hurricane-resistant glazing. This is rated for a specific mile per hour and for debris impacts. Each manufacturer that tests this glazing will specify a certain number of attachments around the perimeter of the glazing. What happens when you have multiple panes of glazing together? Well, sometimes you need to add a structural attachment. This is an example of a plate that was between glazing elements that this glazing edge can connect to with the attachment that's required for the hurricane rating. When there's a larger space available, you can use a tube. So there's a tube on the left, there's a plate on the right. These have slip connections so that they don't transfer gravity load to the plates from the floor above and buckle them in compression, but they have the bending capacity that's required for the load for the hurricane-resistant glazing. This is an example of an elevated structure. You're allowed to have stairs that extend below the design flood elevation and remain in place. This is an open riser so that the flood water can flow through. This structure is elevated. On the next slide, you'll see that pier. It's actually not a solid concrete pier because that would attract too much flood load. There's actually a breakaway panel in the middle that would be knocked out in a wave impact or in a flood, so that only the concrete on each side is subject to flood loadings, reducing the total overall load on the structure. This is an example of a finite element analysis model. This is glazing with mullions, looking at the stiffness of the system and how much it moves, because the more it moves, the less the force the impact load imposes upon it. This is looking at the stress in the glass to make sure that when you're subjecting it to an impact load, you're not exceeding the glass capacity. So those are a few structural items. Now I want to talk about where the code's going, what's happening next. So historically, everything in flood has been based on NFIP. So the National Flood Insurance Program started after Hurricane Betsy. People were sick of having flood losses. The government stepped in to offer this program. You pay for insurance, you can have your losses covered. And the program was fairly successful initially. As you can see, up until about Hurricane Katrina in around 2005, the premiums that the program took in covered its losses. Now, there were operating expenses that aren't included here, but the program was somewhat sustainable. But in the last 20 years, we've seen these huge storms that have had huge losses, and the program has been totally underwater financially. There's been some congressional bailouts, but the losses keep mounting. So it became clear that the 100-year flood is not a sufficient design target. So ASCE 722 committee took this up. There was always a desire to increase the resiliency in design for flood loads because the losses were not proportional to other loads that we designed for. We're designing for the 100-year flood. We designed for a typical building for wind to the 700-year flood. In terms of the losses that the National Flood Insurance Program sees, 1/3 of them were in the V zones, which is like right on the coast. 1/3 of it was in the A zones, which is the next inland areas that are subject to flood designs. But another 1/3 of the losses were in X zones and shaded X zones where there's no design requirements at all. So ASCE 7 determined that for risk category 1 structures, these are your garages and barns, that the 100-year flood is likely sufficient. For a risk category 2 structure, this is your typical building, a residence, office building. The design shifted to the 500-year flood. For risk category 3, so like a school, to the 750-year flood. For risk category 4, to the 1,000-year flood. Now the flood maps that we have all show the 100-year flood. They also show the shaded X zone. This is the 500-year flood. It's the area that has 1 foot or less of water in the 100-year flood. And so in order to have this be enforceable, the area of applicability was set to the 500-year floodplain. So if you're in a 750-year flood category for design, there's no map for 750-year flood. So if you're outside of the 500-year flood area, it's not enforced. You might want to consider designing for, looking up your topography and seeing if it would apply and designing for it anyway. But in terms of practically the information that was available to practitioners, the area was set to the 500-year flood. With all of these changes, the committee's also looked at formulas for loads and formulas to help people find what these elevations are if you don't have the information. So this is an example of a flood map. We've seen this before. This is from the FEMA Map Service Center. So you can see that the orange is the 500-year flood and the blue is the 100-year flood. And in some areas, the 500-year flood is like totally surrounded. And this is usually the difference of about 1 foot of elevation, right? The 500-year flood has 1 foot or less of water. And so you have these areas, high density areas in lower Manhattan that don't have any protection requirements, whereas the building next door to them has to add 2 feet of freeboard. And that's a more restrictive design than, this elevation is actually lower than that site plus 2 feet of freeboard. So it didn't make any sense that the 500-year floodplain didn't have flood load design. This is an overall view of New York City, just so you can see the extent of the area that would be affected. This is around the airport. There's a lot of residential areas in Brooklyn that are in the 500-year floodplain, and then smaller areas of applicability along all the coast. When we look at the probability of flooding, one thing we have to think about is, you think 100-year flood, oh, that's, it only happens every 100 years, that's rare. But you have to add the number of years that your structure is going to be in existence or present. So if you're looking at a 100-year flood, if you have a 50-year service life, there's a 39% chance you're going to see the 100-year flood. Whereas if you move to the 500-year flood, there's a 10% chance that the building will experience that flood. one thing that the committee for ASC 7 did was try to create scaling factors. We worked with the Army Corps of Engineers who have done these big comprehensive studies, and we looked at different regions because we were able to fine-tune the coefficients based on where the sites were located. So it's different if you're on a river versus on a coast. But for the 100, 500, 750, and 1,000 year flood, we created these multipliers. If you know your elevation under the 100-year flood, you can use this multiplier to get your elevation under these higher return period floods. All of these calculations are based on the still water depth. The number on the flood map, on the FEMA map, is the top of the wave. And so it's hard to scale the top of the wave because everybody has a different water height and a different wave height. Sometimes the wave could be a foot and sometimes the wave could be 8 foot. So all of these scale factors are based on the still water elevation. So where you're used to going to the map, now you're going to go to your flood insurance study. So the flood insurance study has the still water elevation for your 10-year flood, your 50-year flood, your 100-year flood, and your 500-year flood. So you can find the elevation of the still water at your 500-year flood, and you can calculate the wave load that your site would experience on top of that. The standards also added a requirement to consider sea level rise. And right now, as this is the first time it's being incorporated into the code, this requirement is only for the minimum historic rate. So you take what the past sea level rise has been and you just extrapolate it forward. If the polar ice caps melt, these numbers get blown out of the park. But at least there's an initial idea that we should be looking at this, we should consider it, we know what the past rate is, that's the minimum we should use. So if you take a look at a coastal transect, you're going to have your still water elevation for your return period. You're going to add your sea level rise. You're going to compute your wave. And the top of that elevation is the equivalent new design flood elevation. ASCE 7 also modified the formula for velocity. Velocity of water impacts the hydrodynamic force that is applied to your building. So in previous editions of ASCE 7, it was only in the commentary, and the commentary only referenced this FEMA lower bound and upper bound. With the Army Corps of Engineers, we plotted the velocities at many different sites, and this is the upper bound line. So you can see that upper bound line is really conservative. There's hardly any points that even approach the upper bound line. Most of the velocities were lower than the upper bound. And so we, for ASCE 722, that upper bound of velocity is cut in half. This is the new load, and then there's limits based on your risk category of how far to extrapolate that line. Another item that was added in ASCE 7 is debris damming. Debris damming is if your columns are so close together that you start having debris piling up against them. So there's a consideration that you need to add hydrodynamic loading if your columns are spaced closely together. If your columns are less than 10 feet spacing, you need to consider that 70% of the area between them could be blocked by trees and cars and debris, and that serves as a sail area for a load. If your columns are 30 feet apart, you don't have to consider that you're accumulating any debris because they're far enough apart that the debris can get through. There's also revised formulas for wave loads, and then before the wave load was just a force. It's a force that was applied at the still water level. You kind of had a single number for. Now there are pressure diagrams. If the wave goes over top of your structure, you can truncate it. If the wave goes underneath your structure, you can truncate it. So there's new formulas to go with all of these new return periods. There's also a requirement for what the debris is. And for bigger buildings, there are bigger debris. So if you have a risk category 3 or 4 building, you might need to consider that it's hit by a shipping container or a barge. And we look at this requirement is not applied everywhere. It's applied based on where your site is located. So if you're near a shipping container yard, there's a radius that your debris can travel over water, and there's a radius that your debris can travel inland, and that depends on the density of the environment. But there's now much more guidance on what the debris loads for buildings are that's within the code, not just within the commentary. So that was kind of from the engineering side, ASCE 7. ASCE 24, setting the elevation that buildings are elevated to, that the floors are at. This effort came 2 years later. By this point, FEMA had kind of gotten totally on board and supplied a lot of engineering assistance to try to figure out, we have these multipliers in ASCE 7, they're helpful for determining loads, but can we be more precise? Can we try to find the floor elevations, and can we make it so that you don't have to calculate the wave loads or the flood in order to figure out what elevation to set your building at? And so they look complicated, but there are these charts, and it's kind of like the more you know, you use the most amount of data that you have. So if you have your 100-year, 500-year, 750, or 1,000-year flood data, you can just use that. If you have a coastal engineer who's given you that data, if it's published in a study, you can use that number. If you only have your 100-year and your 500-year data, you can take the proportion of those two. So they kind of look at the delta between the 500 and the 100-year storm, and there's a formula based on those two numbers to figure out your elevation. If you don't have any 500-year data, there's a multiplier with only using your 100-year data. And then if you don't have any data, there's a separate multiplier. With all of this, there's a study on the reliability, right? So when we design buildings, ASCE 7 has a standard. Under an extreme hazard, only a certain proportion of buildings should collapse. We knew that the standard before didn't meet that. One item that was in the old standard that was trying to address that is if you were in the V zone or the coastal A zone, you had to multiply your flood load by 2. Even in an ASD case, the load was factored, and it was because we didn't know. We knew that the number wasn't reliable enough. We knew that buildings were going to be flooded. We knew that the 100-year return period wasn't sufficient to meet the collapse proportion. Once you drop to the A zone, that load combo dropped to 1. So all of a sudden, if you are building that's situated between a coastal A zone and a regular A zone, you lost reliability. And then once you got to an X zone, there's no design for flood at all. With the new changes in ASCE 7 and ASCE 24, that reliability diagram is much more smooth. Right now we're using the 100, the 500, the 750, and the 1,000-year flood. We're calculating the depth at each site. And the only drop in reliability happens at the 500-year flood boundary, where we stop considering flood loads, just because of the nature of what we have mapped and what we can use. All of these standards are available for free. One benefit of having the supplement come out after the standard is they had to publish it as a kind of like an errata online, so you can download ASCE 7 Supplement 2. FEMA made a building designer's guide as a complement to that, with examples on how to apply it. And ASCE 24 is out for public comment right now. It's available until September 26th. So if you want to see the changes in ASCE 24, you can download it for free in the next 2 weeks. It'll be out by the end of the year. And then this is just what's to come. All of these numbers are multiplying flood loads by scaling factors to try to determine what your new flood elevation is at different MRIs. FEMA knows that they need to actually just provide you that data. So they have this future of flood risk data set where they are trying to make it a probabilistic approach, considering stormwater, considering river and coastal scenarios, where you can get the actual data at your site. This is a couple years away. They're working on the first pilot projects now. Probably within the next 5 to 10 years, it will be available nationally. So with that, I'll pass it back to Leonida.
Hi again, everyone. I know we're eager to jump to our panel discussion, but before we do, I just wanted to navigate us through some other enclosure-related design considerations. So as a reminder, right, we said the historic trends are increasing for winds and storms, and I'm sure you've all seen in the news, you've gotten your notifications about storms, be prepared, wind warnings, you name it, we've been seeing more of it. It's common these days. It's reality. So for most buildings, when we have an increased wind event, right, what do we end up with? We get broken glazing, there's cladding damage, you might have your roof system blow off. You could also get damage to your exterior equipment. And minor to moderate building enclosure damage, might be okay, but the minute you get rainwater entry into your building, you've now exacerbated the problem, and it's much harder to deal with after the fact. Just a note that from wind failure structural systems, it's unlikely for new buildings. In New York City, we're already required to design those up to 117 mile per hour winds. So it's more the components and claddings and all the other things, not the primary structure. So, in this example, we have a building, it's a 50-story tower in downtown Brooklyn. If we were to design, one option is to design per ASC 722, your minimum load requirements, but there's another option to do a wind tunnel test. So we had to decide which we would use for our project. The shape of the building is a little unique. I mean, you wouldn't necessarily say that it's a rectangle per ASC 7. It has some corners, it has, it comes in at places. But what we were most worried about is that there's an adjacent structure, it's actually on the backside of this building, an arena you might be familiar with in downtown Brooklyn that has a very interesting curved roof. And we were worried about the effects from wind over that roof and how that would affect our building. We convinced the owner to do a wind tunnel study. And this is, if you haven't seen a report with outputs, this is an example of one. I don't know if you've already spotted the highest value here. I'll help you out. It's actually not on the higher floors, which is typically where you would expect higher wind loads. It's at the lower floors, thanks to that adjacent roof. And we're hitting loads of about 100 on that corner. So this is just an example to, you might be safe code-wise to use ASC 7, and that's okay, but it should really, as designers, we should consider the unique shapes of our building and the unique shapes of adjacent buildings and how that can affect our structure longer term. And here's just some examples, right? Broken glazing. We have, full cladding failure off the building is a possibility with high winds. And then if you have unreinforced masonry, you could just have total loss of your facade in those cases. We have examples of wind-borne debris through glazing, as well as wind-borne debris just attaching itself onto your structure. And in many of these cases, if it's, coming through the cladding like this, it might not be addressed, or ownership might have to figure out how to address it so that they don't have fear of it falling on someone at a later date. And the risks are real, in case you're wondering, right? Like, there are news stories out there that talk about these things. This is from a recent storm a few months ago out on the West Coast where tiles flew off a balcony. Actually, this is a snip of a video. I didn't think the video would work, so I took it out. But there's actually a portion of this where they're videoing the tiles, but on the other side, there's a couch flying off of the balcony because someone just had, furniture outside that wasn't meant to be outside or whatever the case was, and the wind loads were high enough that that became a problem. Luckily, no one was hurt, at least per the videos I saw. And, when we think wind-borne debris, if you're designing in Florida, it's the first thing that comes to mind, right? But here in New York, we're not necessarily trained to think about it immediately. But what's interesting is that recent code changes have updated things in New York City. So it's almost kind of hidden, but if you're risk category 3 healthcare facilities, you are now affected by wind-borne debris design requirements. So if you're within a mile of the coast, but if you picture Manhattan, right? Like, here's an example. That's, my company's office in Midtown. We're on 7th Avenue. We're, within a mile of the coast. So if the building was to change use and decide to become, healthcare, we would need to see how we're affected. If we were going to decide to replace the windows, those new windows would now need to be wind-borne debris resistant. So just something to, keep in mind as you're designing around New York City. Jessica touched upon it briefly, but wind-borne debris, right? Laminated glazing is a way to counter wind-borne debris requirements. It also has other benefits as safety glazing. It has post-breakage performance, so it will actually stay on your building and will keep water out after it's been broken. And if you need acoustic requirements anywhere, you want a better performing building for acoustics, laminated glazing will help you there as well. In terms of, you can specify tested systems. There are many out there. Fortunately, there are, like I mentioned, Florida and other states that are kind of ahead of us on this, and they've had requirements for tested systems for a long time, so there are things out there. Something to note is that it's generally accepted to get some water leakage, even in these tested systems, if you have long periods of combined high winds and rain. So that's something people kind of miss. The standards and the codes do allow that. And then just a reminder, if you do have broken glazing, it's not just about the water entry within your building. Once you have openings in that building, it behaves differently, and you're actually adding wind load to your remaining walls and your roof because you're allowing that wind to enter into your space as well. So this could lead to, roof blow off or other damaging aspects. Speaking of roof blow off, here's an example of what that could look like post a storm. The photo on the right actually shows some deferred maintenance. So if you could see in the background, there's some sandbags. Those used to also exist in the front of the photo pre the storm. So this wasn't something new on this particular building. They knew they had issues and that their roof had started to unadhere or come undone. But they kept deferring maintenance, and eventually in the next storm, not only did the roof blow off, those sandbags also became flying objects during the storm, which just caused more trouble. And with pavers, it's a reminder that the wind flow through that gap can uplift your pavers. And what that could look like is they could uplift and it's just a mess to fix later, or it could uplift and again become flying objects for your glass railings or your glass at the terrace if you have curtain wall, or for your adjacent buildings and your neighbors. But there are standards out there, so I didn't mean to frighten anyone, right? I just want to bring us all to the reality of what can happen. But there are guides that can be followed. So for your roof assembly, there is a free software out there, RoofNav. It's from FM Global, the insurance company provides it, and it has a list of tested roof assemblies. So if you know your wind uplift and common is to have a safety factor of 2 in the industry, you can find assemblies, whether they're adhered, mechanically fastened, depending on your deck type, that can meet your project requirements. So just make sure you're specifying systems that will meet that or put the requirement in there for others to give you the documentation. There is also testing that can be done to make sure that the roof you're getting installed is actually meets those standards and those uplifts, because it's one thing what's been tested in the factory and it's another thing of how it's installed. So these are things you can specify to make sure that the building owner, the client, they're getting a roof that doesn't have to worry about these high wind conditions. And just as a reminder, the wind loads are typically higher around the perimeter of a roof and at corners. So these are locations where detailing is very important. If you notice here, we have these continuous peel stops. This can help avoid your roof blow-off situation. So if you were to get the roof from peeling on the edge, at least with peel stops, you won't have the damage come across your entire roof system. And manufacturers can help you work through these for particular roof systems. So in terms of coping, it's important to specify a pre-manufactured coping system. Common practice has been to just have your roofer install some sheet metal and put some fasteners in. Who's responsible, where are those calculations coming from, how often are we fastening our roof system in? There are products out there these days that have been designed and tested to meet all these wind requirements so that that burden is off of you, and you don't limit yourself to your roof installer if they don't have the capabilities of providing these calculations for you. ANSI SPRY ES1 testing requires you to pull on the top of the coping and the edge of the coping at the same time. And this is kind of an example of what those tests, like what vigorous tests these coping systems go through. Similarly, there's ANSI SPRY requirements for your paver systems that also get tested, so you can hopefully avoid some of those earlier photos we saw and the news of pavers flying off of balconies. And these will test the spacing between systems, and you can use those values in your design. Similar standards for vegetative roof systems, right? These are, again, situations where you can have your vegetation flying off in high wind. So even if your roof itself, what's under the vegetation, is designed for a high wind situation, we need to make sure that the vegetation that goes on your roof is also designed for that. Consideration for rooftop equipment, right? It's the same thing. How is the load being transferred from the PV panels to the roof? All those connections should be able to withstand the same wind that your roof is being designed to withstand. When you specify your roof system and some of these things, you can require calculations for the MEP equipment back to the roof curb to make sure that all of that is being considered. And of course, it's also about maintenance, because if you see some of these pieces of equipment that have gone flying, they're a little rusted, so it's possible that even if they had the right amount of fasteners in the first place and they were designed correctly, they've just rusted out, and that's why these things can go flying. So that kind of concludes the enclosure portion of the discussion. But when we're implementing these things, right, we have to consider the impact on recovery. I kind of alluded to that early on, right, because that's part of resilient design. It's not just what we're designing to, but it's how does the building recover and how does our community, like how does New York City recover from this, right? That we're helping with that effort to make sure we can survive these events and get through them with a little less burden. So, if you're designing a resilient building, you're helping design a more resilient community. And as designers, we're the thought leaders, right? So we have a collective responsibility to design these buildings for generations to come. I know Jessica mentioned 50 years, but realistically, these buildings that we have around us, right, they've been here longer than 50 years. We want our buildings to be around longer than 50 years. So, we have to take into consideration, we know the codes are getting there, but they're not there yet. So the more informed we are, the more information we can provide to owners, and, get ourselves to the future. So that's it. We're going to do a bit of questions in a panel discussion forum, and then we'll open it up to the audience for any questions you guys may have. So think about those questions.
The wireless microphones for the audience are. I'll go try to find them. If you have any questions.
could just like raise your hand and speak up, and we'll do the best we can.
Testing? Okay. So for starters, do you want to explain to the audience some of the challenges you face when designing for these situations? Like what comes to mind? What do you face most often?
I guess I'll start. I mentioned one earlier, the dry floodproofing systems, things that require a whole staff to deploy, and keeping those systems fit and ready for when you need them. I think that's a big challenge. Another challenge I'd like to touch upon is, especially when you're dealing with buildings in flood zones, you see the maps, they keep getting higher and higher and higher, and your building and your occupied floors are getting higher and higher and away from the street. So a lot of times the engagement of the public realm with your building starts to suffer. Buildings are elevated from the sidewalk, and you have pedestrians walking by, and they're walking against blank concrete walls. It starts to kind of create this gap between the public realm and how they interface with your building. And zoning tries to do something about that by requiring mitigating options, designing something to soften that divide between the street and your main entry floor. So I think that from a designer's point of view, that's always a challenging aspect. How do I comply and make my building safe, but at the same time don't alienate the public, such that, and an example that's kind of I see a lot is retail stores. You have a whole street of strip retail, and then certain buildings are forced to comply because they were either damaged or they did enough to trigger compliance, and all of a sudden they have to elevate, and then that retail tenant or that retail space is pulled out from the rest of them who are getting all the customers. So it's an interesting challenge. It's more of a macro zoning and kind of a broader based challenge, which I think zoning is trying to address, but it's not fully baked, and we should think about it as a whole.
Daniel, Jessica?
I think one of the large things is just the magnitude of flood forces. Like I've designed 2-story buildings that have the same base shear as a high rise in the city has for wind load. If you've ever been swimming in the ocean, you know it can knock you down, but the forces are huge. I think one other frustrating thing as a designer is also all of these requirements are coming from an insurance program. And so the requirement of like, you can't dry flood proof a residential space. I want to I am an engineer, I can find a solution. I have a client who's spending $20 million on a house, they can do it. It's a little frustrating that there's not an opportunity to do something outside of the regulations if you design it to the same standard that a commercial entity could design for.
Yeah, I think the most challenging part ends up being your conversations with your clients, is not just doing the bare minimum, right? Here's what's required, and as you've seen, hey, you may only need a deployable flood barrier that you store in a basement somewhere for 5 years, and then bring it back out, and it doesn't work. You try to convince them to take the long approach. Yes, it's probably going to be a little more expensive, but in the long run, it's going to be the better option. And as we've talked about the design elevations raising, right? So you may have set up your system, your barrier system and things to work at a certain level, and maybe they update those in 15 years. And hopefully, if you've gone above and beyond, you've now future-proofed yourself. And I think that's those are the hardest questions to have during design.
That's great. Speaking of wet floodproofing versus dry floodproofing, Edwin, from the architect's perspective, what's your experience with loss of below-grade space and affecting programming? Like, how are your clients, handling that?
That's a big one, especially in dense urban areas like Manhattan. I know that once Sandy hit and FEMA decided to publish preliminary maps based on actual data from Sandy, it was going to make a lot of areas of lower Manhattan, subject to flooding, and also if you apply the regulations, you can't do a lot of things below the flood elevation. And we know that in Manhattan, there's a lot of prime retail space that's below grade, concourses, shopping centers, and you're talking to, and the real estate lobby and industry leaders are very powerful. So they actually stopped the pre-firms from becoming effective maps, and they held it off somehow. But that's the loss of below-grade space is real. I mean, and you have so many legacy conditions in cities with a lot of history, like Manhattan. And again, it's a broad-based challenge. It's a very and telling even a small homeowner or a small building owner, like, you can't do anything downstairs. They're like, what do you mean you can't do anything downstairs? I was ready to do all this and that in the basement, and it's a very real thing, and people need to grasp it.
Thanks. Daniel, so when we're, dry flood proofing with our glazing systems, you mentioned tested glazing systems. What's the current availability? Is there somewhere we could find, what's been tested, or manufacturers advertising,
Yeah, so there are. I mean, I think some of the manufacturers are catching up on this, and they're taking some of their standard systems. I mean, some of the companies you're used to working with, I won't go through a list here, but they have published data where they've done testing, right? So that it's available. Particularly, they've done it over the years for the Florida markets, and now it's becoming applicable here. But they're available. They're certainly available. They're not every company's going to have a one to offer, but they're readily available. It's not a kind of one supplier thing anymore. So.
And Jessica, what about, so you mentioned all these regulations. When do you think they're going to be adopted? Like, do we have a timeline for that kind of thing?
So ASCE is promoting the ASC 722 Supplement 2 and ASC 2424 for IBC 2027. So for communities that adopt the IBC, it's usually a few years after the IBC is released. There are some initial proposals submitted to New York City Building Department in the current code cycle to at least consider the loading part, that the buildings are designed for the loads for the higher storms. Because ASC 2424 doesn't officially come out until the end of the year, there was no proposal submitted to consider the elevation, raising the floor levels portion, but it's a potential that the loads could be there even prior to 2027.
All right, so we'll all look out for that. Are there any questions from the audience? Do you want to speak loudly, or do you want to come to the mic? Oh, we got a mic, okay.
Okay, this is really, really esoteric, complicated. Peel stops. Tell me exactly what they are. Are they a piece of plastic screwed into the
Yeah,
end
or
of the
metal,
membrane?
depending on the manufacturer. But yeah, the intent is that it's also mechanically fastened, so you have something else to rely on than just the adhesion. And if it does start, the roof starts peeling off, you'll have a stopping point. So sometimes they're even just required in the field of the roof. If you have maybe a high slope application, manufacturers might recommend that you put them in. But they definitely come in handy for high wind uplift.
It's screwed in. Okay.
I've got so many questions, but I'm going to do one by one. So I'm an architect, and I do a lot of waterproofing. We had a project for a large residential developer on the waterfront in New Jersey, and it was right, close to the water. The DFE, they decided to move all of their inhabitable spaces above the DFE to sort of get around the issue of having to deploy wet proofing or dry flood proofing, which are ASC designations, right? So I looked up the definitions of all these, and the difference between dry flood proofing and wet flood proofing is that dry flood proofing will allow for a certain amount of water to seep in over time, right? In sort of a flood emergency situation. Now, In my role in the project, I was trying to determine whether or not their foundation needed waterproofing. And the DEP permit document specifically used the word waterproof foundations required, right? If you're within the floodplain, you need to have waterproofing up to the DEP line, right? Which when you think about it, it's a different, it's like a third category, so to speak, right? Because you're designing for a permanent condition to resist hydrostatic forces from groundwater that are present, right? And of course, the owner was kvetching about how expensive that was, and they didn't want to do it, and they ended up specifying, or they ended up ordering us to use a vapor barrier, right? And we, basically said that this is not compliant because it's not waterproofing in the industry. So in your mind, I mean, you're dealing mostly with dry floodproofing and wet floodproofing, but are there cases where you want to carry on that waterproofing layer in the foundation and connect it to your dry floodproofing systems above? I'm not sure if I'm making sense.
So what I'm hearing is your question is, how does that groundwater waterproofing for the foundation, where does it transition to above grade waterproofing? Is that the question?
That's part of my question. I guess the first question is that the DEP as a compliance body has that has waterproofing as a requirement, right? And the owner had always thought in terms of dry floodproofing or wet floodproofing, and they were fine with dry floodproofing. But we made the point that waterproofing is distinct from dry floodproofing because the definition of dry floodproofing allows for water to seep in over time. Whereas if you're designing for hydrostatic conditions, you have waterproofing, right?
Yeah, I think dry floodproofing, right? Its intent is to not let any water in. That's its intent.
Yeah.
But the code allows for a minimal amount because it knows nothing is perfect.
It's 4 inches an hour.
Yeah, correct.
Yeah.
Correct.
So, but as a consultant that specifies waterproofing systems, you don't want any water at all, right? So, I guess the question is, when you are consulting for clients who want, say, a waterproof basement, and then above grade, the DFE is 2-3 feet above the grade line. Those are two distinct systems, are they not? Or are you trying to make the dry floodproof zone also waterproof?
Technically, it's dry floodproofing is not just above grade; it is below grade as well.
Okay.
So, if what you're describing as a basement that your client wants to keep water out, it sounds to me it's a dry floodproof space. So, it's going to be basically a bathtub, like a concrete bathtub. Your foundation walls, your slab on grade, below grade, has to be designed for buoyancy, for waterproofing. Not just the water pressure of groundwater, which is part of it, but there's going to be forces on it, and you're required to protect up to that minimum standard the code says, which is the DFE. So it's a continuous envelope of keeping the water out.
Okay.
I mean,
So you're considering it.
Even if you're an open foundation, you have to consider protecting the elements from corrosion. I'm not sure if you don't have a basement, but if you have concrete and you're on the water, you might want to consider waterproofing within the concrete, like a admixture that can protect the concrete, corrosion inhibiting admixture to protect the rebar,
Yeah.
Additional cover.
That's interesting because the civil engineer on another project had said that that's all that was required, and you didn't need to have a membrane on the outside of the. I'm changing the subject now, but.
I think it depends on the project, right? That's to your point about, is there a basement or is there no habitable space below? Is it residential, commercial?
Yeah.
It changes how you respond to that topic.
But
Right.
if the goal is to dry floodproof, you're going to want to, like Edwin said,
Bathtub, yeah.
bathtub, and you're going to want a good transition between your below grade to your above grade, as you would, on a project that's not considering flood, right? But especially in a flood situation, you want to make sure you have a transition so you're not accidentally letting water in where those two are meeting.
Right.
And you don't then want water, flood your basement and, it'd be a wet condition that wasn't designed for,
Right.
so.
So I'm sorry, I just wanted this, because this is very interesting when you said about the admixtures. So, among the three of you, is that considered waterproofing for a foundation? If you had an interior, if you had a below-grade space and you wanted to waterproof it, do you consider admixtures as a good instead of
I
waterproofing?
was going to say, as an enclosure consultant,
my
I have a
favorite. I was
very
ready.
strong opinion
Same.
that
Same.
that is not
do I.
considered waterproofing.
Right.
If it meets the structural engineer requirements for protecting the concrete and the rebar, that's one thing. But if you're going to occupy the space in the basement and it needs to remain dry, you need a designated waterproofing layer.
Right, yes, that's
I've had that conversation with so many people, and it's frustrating.
Yeah. Thank you. Very interesting.
What about local flooding? You know, some of the words which came out, like when you were saying like flood proofing, so, is it like flood proof or flood resist? And also like most of this is about water level rising and from the ocean and things. But there's everywhere around the world, around New York City, is the local flooding. The streets gets flooded because, and you have just like an hour of rain and everything is flooded and the basements are flooded, the roofs are, the windows are leaking and all of that. So
You're talking
yeah.
about stormwater from flash floods and thunderstorms.
Exactly.
And it's exacerbated in an urban setting where your pavement, your asphalt, or the streets, your ground is not pervious, so everything collects very quickly. And if you're unfortunate enough to be at a valley point where there's ponding,
Yes.
right now,
we all know that. And what is happening is this is increasing. September, October, July, whether that's 2024, 2023, anywhere like we are looking at our neighborhoods. So we are not talking about global warming and the 100-year floodplain. We are saying year after year, our local flooding and that phenomena is very clear and present, but I didn't hear anything about that. So what do you think?
yeah, I kind of showed some maps of, the city is making efforts, both in government and also private public organization groups, to start to map the storm levels based on grading, based on increasing frequency and intensity of flash flood thunderstorms. And for every local project, the code currently only requires that you calculate your developed storm flow from your own site. It doesn't factor in like, what if the whole street's water from 2 blocks away starts running into my property? What do I do? That's not there yet in the codes, but I think you're very correct. It's a very
At the same time, there are two things. So one is like, the mayor would issue this emergency recovery, you know, they will declare that, and usually that's in the case of flash flood. So this is at the city level. But at the same time, IRA, the Infrastructure Act, so out of that we have the Climate Mobilization Act, and we have a 360 billion. So from the point of view of climate readiness, so this localized flooding, they have outlets. So this is under the weatherization, and in that, you raise your, basically like if you have boilers or things. So basically there is funds to raise your, what you have to do is when the emergency is declared and there is a flash flood. So then like you register, you reply, and you get, and then like, you get some technical assistance, but at the same time you get, funds to actually, do some little things so that you can protect yourself from the flooding. And that is something which is very clear and present. And I would say which is existing, because we are not designing anything new, like whatever is existing, so get that climate ready. So that's what is the part of the Climate Mobilization Act. And then, so it's clear and present about the weatherization, which is whether your windows or whether your walls, whether your basement, whether your equipment, electrical systems, pumps, boilers, and air conditioning, all of that.
I mean, I guess a few things with that. There's no design requirements if you're in a stormwater flood zone right now. Those maps are fairly new. There may eventually be design requirements. From a citywide perspective, I was at a DEP breakfast a few months ago, and they've made this entire model computerized of the city's stormwater system. And so I think that they're, looking at it from a city level on where can we make interventions and where, they know the areas that are low-lying, that are prone to flooding, the alleys that get flooded every time there's a major storm event, the water that's coming up through the sewer system, it's not even water like running off your yard. At some point, some of these locations, the stormwater system can't handle it. You've got backflow up through your pipes in your house. So I think there's both if you're a homeowner and you experience that, you adapt. My basement had a foot of water in it like 3 years ago, and now my washer and dryer are, elevated on 3-foot pedestals because the machines died in that event. But homeowners adapt, and the city, I think, is trying to address some of those areas. And as technology gets better, they are able to actually see. Besides just seeing where the floods happen, they're able to play with the models and try to do limited interventions at spots where it might make a difference.
Yeah. And in the code stuff and the things that they're never going to be out as fast as we need them. So I think a lot of it is put upon the design professionals to make good choices, right? So it's this, in existing structures that aren't being renovated, that's a little more complicated. But in new construction, alterations, renovations, study your site, study those things. Hey, I know I'm in a low-lying area where that could happen, so maybe I don't make this design choice. I don't bring glazing down to the ground. I don't do things like that. It's kind of thrust upon us to help our clients with those choices, even though there's no mandates to do certain things.
And I think informing them is important too, because they may not be aware, they may not have thought about the property or the slope that's next to their building, and the fact that the water could be coming down and could be rushing by the time it gets to them, right? We're more aware, we see more things. If some homeowner is renovating their 100-year-old building, it may be the first time they've ever interacted with an architect or a designer, and whether you're spewing code at them or not, it's not going to matter. It's more, they're going to care if their washer and dryer needs to be 3 feet up off the ground, right? Or if they were planning some high-tech, below-grade, space, maybe we need to start talking about interior drainage and, other things that are not code requirements, but would help them. I saw your hand up too.
Hi. So a lot of the materials and technologies discussed are involved in very carbon-intensive processes like steel, carbon, concrete. Do you know of any technologies that are being developed that are sustainable or are involved in the circular design process?
I think it comes down to strength of materials in some of these cases, and most of the sustainable materials that I can think of either don't want to be immersed in flood situations, or because they could fail during the event, or aren't strong enough to withstand some of these loads that we were talking about.
I mean, the steel industry would argue that they are sustainable because about 97% of steel is recycled. I know they make a lot of arguments that wood isn't as good as it makes itself out to be. You can look at some AISC documents on that. But I mean, things like glazing, it's a pretty small assembly. You have a foot of concrete versus you have a flood-resistant glazing that's an inch thick, you know, in terms of the material and the transportation, and I feel like even just designing glazing systems, it's a lot less bulk of material, and so that has benefits.
I think part of the sustainability too is, you know, will it withstand, but then you need to replace portions of it after an event, or is it going to withstand and, you know, stay in place? So, you know, concrete is maybe thicker and there's more material, but I wouldn't imagine something would happen, whereas we discussed that glazing could crack and, you know, then you have to replace it. So there's kind of a lot that goes into that sustainability conversation, I think, throughout the industry. I know you have your hand up, but you already spoke. The gentleman in the back, I think, has his. I think this may need to be our last question.
Hello, everyone, and thank you for putting together the panel. I'm new to the AEC industry, coming from software, and I was wondering about the retrofitting. I heard about the last hurricane that did damage to the city, and I was curious, are you seeing trends in clients or developers asking for more retrofitting solutions for their projects? And secondly, is there an incentive structure maybe with the DOB or the government that would have these renovations or new constructions use better reinforcements for waterproofing or windproofing?
Well, unfortunately, I think a lot of times it's, at least with most in the New York City area, it's make me do it, right? They're not, unless they've suffered, like after Sandy, right? Sandy was a thing where it had to happen for people to start doing these things, and unfortunately, I think that's a lot of it, especially on your larger scale stuff, right? Not necessarily your residential work, but your more commercial office buildings, your large residential buildings. It's if you're not going to make me do it, I'm not going to do it right away. But there are some forward-thinking owners and developers out there who are investigating that or are asking those right questions. It's just not as many as it needs to be.
I will add that as far as incentivizing owners to do certain things from a zoning point of view, they've kind of started to think about this, and they made certain wet flood-proof spaces like exempt from floor area calculations. So if you chose to make your building resilient on the lowest level, you get that, you recoup that floor area back. You can add another story, you can build more square footage. So I think that's one thing I see that's in practice now is you know, you get to do more if you spend some money to protect the lowest level.
I think the other incentive, the reminder, is that it will affect your insurance premium. So if you can show that your building is resilient to these, you have more options for insurance and your premiums should be lower. And along with that, you can probably charge more for your retail tenants if they don't have to worry about, you know, their space and their merchandise or whatever it may be flooding and having to recover after this event. So there are some things, you know, to consider. Obviously, we're not the ones doing those calculations on the back end typically, right? But we can get them thinking about it, and maybe they'll find the math and it'll work to go above and beyond a bit. All right, so I guess bringing it back just to close on one last question, what's one key takeaway you want to make sure the audience remembers from the presentation today?
I guess I'll start. When you have a choice of choosing systems that need installation and deployment by staff versus a system that is kind of automatic, I usually recommend the automatic version. It's just that, you know, human beings, they're so unpredictable. I've heard stories during Sandy when people are trying to call people to come install their flood shields. They're busy going home to protect their own house. Or the shields are just, you know, too far away to be here in time. They're stored off-site. So it's just so many variables for failure as far as, you know, systems that require human intervention. I would always recommend to a client, let's consider this first, unless you really, really want to, you know, use that below-grade space, or you know, you're thinking that it's not going to happen that often. But that's usually what I would kind of recommend as far as building design, passive systems.
I'll add to that is that I had a client not too long ago who had a building in Lower Manhattan, and they had these beautiful brand new deployable flood barriers for their building, but they were storing them in Astoria, and they didn't get them there fast enough to do anything. So the DOB found out about that and then said, no, you need to store them on site, please, thank you. But Edwin kind of stole mine since my entire presentation was about the automatic solutions. That was what I was going to say, but that's okay. Yeah, definitely, I'll second that. But what I'll also say is be proactive, right? As I said before, understand your sites, understand the limitations that you may have in your project, and advocate for those solutions up front. Yes, some of them are going to be more expensive, and some of them may adjust your design in a way that you didn't necessarily want, but in the long run, it's the right choice.
I guess I would say that the 100-year flood is not this magical line that, like, if you're in it, you design for something, and if you're out of it, you don't. That it's the probability of experiencing it is way too high, and that we should all be thinking of these higher return period floods, but also just looking at the probability of risk. I feel like if you tell someone you have a 30-year mortgage, there's a 25% chance you're going to see that flood in the lifetime of the structure, in your lifetime of your mortgage. It's people, once they see that probability, are going to want to protect higher. So just know that bigger storms are coming.
It's that misunderstanding that you're only going to see it once in 100 years, and I don't have 100 years left, so not my problem, kind of thing. But yeah, I would just say for the passive systems, encourage your clients to have a maintenance plan and a testing plan in place, because they're great, but just like anything that is automated, something could go wrong if it hasn't been used in a while. Something could be disconnected. Who knows? So things to keep in mind. Also, I would say backup power if they require power, because typically power tends to go out in these events, so it's important to think about it big picture. I think.
What's actually happening is currently, to answer some of those things, like LL97. So any building which is like more than 25,000 square feet, like now you have to do this decarbonization. So this is actually looked at as a penalty, and then like you think that this is about energy and passive or like efficient electrical and all that. But actually, like in that there are a lot of components which is about climate readiness and weatherization. So I think if you look at LL97 not just as energy and decarbonization and electricity, you will actually find that there are a lot of incentives and within that for weatherization and flooding and waterproofing and.
Yeah, there are other aspects of climate change that were up there, like extreme temperatures is an example that is directly linked to LL97 and a lot of the sustainability, as well as air barrier continuity requirements. We'd be here probably for an all-day seminar if we touched on all of them. So on that note, thank you for sticking around. I know we went a little over.